coming, and a very large thank you to Claude Sirlin, who, we're getting some reverb here, who came up with this idea and is gracious enough to share even a small amount of his knowledge with us today. Claude, thank you so much. We are very excited to listen to you and learn from you.
Okay, well, thank you very much. I don't know really was my idea or not. I don't know exactly how. I don't know, like that Talking Head song. It's like you might ask yourself, how did you end up in this place? So I don't really know why I'm here right now, but here I am. I gave a series of. I suggested a series of topics, and Rebecca and Jennifer selected, I think, 7. So we'll try to get through all 7. And they started with things that I'm not that comfortable with, such as MR physics, which is okay, but just be aware that we're starting outside of my comfort zone. On the other hand, I suppose, how does one get better, and how does one learn if one doesn't, push outside their comfort zone? So, pushing outside my comfort zone, let's talk a little bit about MR physics. So a lot of things to talk about in this first lecture. We're going to talk about the electromagnetic spectrum. We're going to talk about B0. We'll talk a little bit about protons. We'll talk about this funny thing called spin, something else called the magnetic dipole moment. We'll talk about M0, precession, gyromagnetic ratio, T1 relaxation, RF excitation, dephasing, T2 relaxation, and chemical shift. So a lot of things to talk about. So let's start with a little overview. So in MRI, we start with a very large, powerful magnet, and we put someone inside that magnet. We send radio frequency waves, energy, electromagnetic energy into the patient. And that patient's protons then interact with those radio frequency waves and send radio frequency waves back at us. And we then make images from the radio frequency waves that were sent back at us. So we've been talking about radio frequency waves. So what are radio frequency waves? Well, shown here is a table that has different frequencies in hertz, different energy levels in electron volts, and different wavelengths in centimeters for energy along the electromagnetic spectrum. And so you'll see that X-rays, that's the stuff that once upon a time you actually learned how to read X-rays. So you'll, every time you do a chest X-ray, that's an X-ray. And there you have photons that have frequencies in between 10 to the 18 and 10 to the 19 hertz, with wavelengths of 10 to the minus 8 to 10 to the minus 9 centimeters. That's really, really tiny. That's really energetic. Slightly lower in the spectrum, you might run into ultraviolet light. And below that, you'll see visible light with wavelengths on the order of 10 to the 5 centimeters. Then you have infrared light. Then you have microwaves. Now you're dealing with energy in the order, or wavelengths in the order of a centimeter, or a little bit less than a centimeter. And then finally we have radio waves and TV waves. And notice that these radio waves and TV waves have wavelengths on the order of 10 to about 10,000 centimeters. So these are the wavelengths of radio waves and TV waves. Well, what does all this have to do with MRI? Well, it turns out that MRI is right here. So MRI has energy in the radio wave and TV wave spectrum of the electromagnetic spectrum. We can also look at it this way. We can put electromagnetic radiation from 3 megahertz to 128 megahertz, and AM radio is a little bit less energetic than that. It's about 1 megahertz. Way over here we have FM radio between 88 and 108 megahertz. And here we have MRI at 1.5T. So MRI at 1.5T is somewhere between AM radio and FM radio, and 3T MRI is twice the frequency of 1.5T MRI, so 3T MRI is here. Now it turns out that 3T MRI is at the same frequency as air traffic control. So one reason we want to shield our magnets is that if we didn't shield our magnets, then our radio waves might start interfering with the radio waves we're sending to airplanes up in the sky, which could result in multiple different catastrophes. At any rate, MRI at 1.5T is approximately TV channel 2, and MRI at 3T is air traffic control. Now I mentioned that we're going to use large, strong external magnetic fields, and these external magnetic fields are known as B0. So shown here is an MRI magnet. This magnet is on the order of 10 to the $6, $1 million. This is my son when he was 2.5 years old, reaching for this little magnet here. That magnet is 0.01 Tesla and probably is on the order of $1. Anyone know what this thing is? This is the kind of magnet that picks up your car at the junkyard. This magnet costs about $10,000 and it's 0.3 Tesla. So notice that this magnet is anywhere from 5 to 10 times stronger than the magnet that picks up your car. Now this is the planet Earth, and in 2003 I did a back of the envelope calculation, and I assumed that, at least based on real estate, the cumulative worth of the land surface of the Earth was 10 to the $17, and the Earth has a magnetic field strength of this. So you can see that if you're investing in magnets, investing in the Earth to buy a magnet, not probably your best investment. And this isn't actually so bad, right? You know, $1.1 million for a very, very powerful magnet. Well, how strong is that? So now let me share a story with you. So in 1995, I was trying to get into the radiology program at UCSD, and I got a small grant to do MRI in the knee. Now I know you're probably wondering, what was I doing MRI in the knee? I don't know what I was doing MRI in the knee, but there I was. My research project was to do MRI in the knee, and my first patient was in a wheelchair. And so back then, the way you did research is someone showed you how to do an MRI, they then left, and then you did the MRIs on your own. So there was no one else there. Is there a problem?
The WebEx is getting a little feedback, so we just need to mute one of the computers. Let's do this.
I think if we just,
Perfect.
All set?
Good.
Okay. Okay. So here I am trying to get into the radiology department at UCSD, and I bring my first patient into to the scanner for the first time. I put the wheelchair on one side of the room, and I start to walk the patient who's having trouble walking, and suddenly off the corner of my eye I see something moving, and it's the wheelchair, and I reach out to grab it, but now it's moving so fast that I can't quite grab it, and it goes straight into the bore of the scanner. And I am now freaking out. My career is gone. I'm going to break this scanner. And just like the mom can pick up the car when the baby's under the car, I got this wheelchair out of that scanner. And I didn't tell anyone about this for 10 years. But the point is that in order for me to get this wheelchair out of that scanner, I had to actually go completely horizontal on this and use all of my strength to pull that thing out of there. It was unbelievable. So the point is that these scanners are really strong, those magnets are really strong, and if you're not careful, had that wheelchair hit the man instead of the magnet, it could have been a total catastrophe. So be careful with these scanners. These are very powerful magnets. Now we use the unit of Tesla, and named after Nikola Tesla, who's one of the great, almost unrecognized intellectual heroes of the last 100 years, or 200 years. And 1 Tesla is equal to 10,000 Gauss, and this is Gauss over here. Gauss was so smart that when Gauss was 6 or 7 years old, his teacher, to punish the class, asked every student in the class to add the numbers from 1 to 100. And how long did it take Gauss to add the numbers from 1 to 100? It took him about 20 seconds. The teacher couldn't believe it. But at the age of 6, Gauss realized that, yes, I could add 1 plus 2 plus 3 plus 4, etc. That's going to take me a long time. Or I could think, what about if I say 0 and 100, that's 100, 1 and 99, that's 100, 2 and 98, that's 100, 3 and 97, that's 100. And he figured out at the age of 6 that he'd have 50 such pairs, 50 would be left over, and it's 5,050. So that's how smart Gauss was. So if you want to have a unit of physics named after you, that's the kind of intelligence you need to strive for. Now, all of us are over 6 years old. I think it's too late for all of us. Needless to say, this may be the Claude-a-thon, but there will never be a unit of physics named the Claude. Okay. Now, why is B0 important? Why is this magnetic field important? Because this magnetic field actually magnetizes the patient. You put a patient in the magnet, they become a weak magnet. And all of the MR signal comes from the magnetization we impart onto the patient. Also, many things are proportional to this magnetic field. So look at all the things that are proportional to the magnetic field. The signal-to-noise ratio, the artifact-to-noise ratio, the precession frequency, which we haven't discussed yet, the chemical shift, which we haven't discussed yet, susceptibility, which we haven't discussed yet, but lots of factors that affect our images are proportional to B naught. Related to B naught, but not necessarily proportional to it, is something called the B1 heterogeneity, which we may or may not talk about a little bit, and also T1 and T2 star, which we will talk about a little bit. Okay, so B0, B naught, very, very important. Now, we need to digress for a second and talk about protons. So protons are known as spins. And why are protons known as spins? The reason protons are known as spins is because protons have spin. But that begs the question, what is spin? Well, spin can be defined as either plus 1/2 or minus 1/2 at the individual proton level, depending on whether the spin is going up or down. But that's still not explaining what spin is. So spin is a quantum mechanical property, which as soon as I say quantum mechanics, that means I don't understand it. So it's a quantum mechanical property that induces a magnetic field. So if the proton has this positive quote-unquote spin, then the magnetic field that's induced by the proton points up. And if the spin is negative, then the magnetic field points down. At any rate, this induced magnetic field, because this is already getting kind of complicated, to make it even more complicated, let's give it a different name. So instead of calling it the induced magnetic field, or instead of calling it the proton-associated magnetic field, let's now call it the magnetic dipole moment. So protons have this quantum mechanical property called spin. This quantum mechanical property called spin is what allows protons to create a magnetic field. So protons have their own little magnetic field, and that little magnetic field is known as magnetic dipole moment. So you can think of a proton as being a little bar magnet with a north pole and a south pole. So if you envision a little bar magnet, you can think of that proton as being a little bar magnet, but at a much smaller spatial scale. Now, I mentioned earlier that protons might have a positive spin, like this one, or they might have a negative spin, like this one. And depending on whether the spin is positive or negative, the magnetic dipole moment either points up or points down. So this turns out that this will be important. Protons either can have magnetic dipole moments pointing in one direction or another direction. So why is this important? Well, because on your left, if you have a little proton just sitting there by itself in the nucleus, then this proton will point up, the nucleus will point up, and you will get a net magnetic dipole moment from the nucleus that's pointing up. But what if you have a nucleus that has two protons? Well, one of them will point up and one will point down, And you might guess that that means they cancel each other out, and you'd be right. They cancel each other out. So it turns out that nuclei that have an odd number of protons, neutrons, or both have a net magnetic dipole moment. So let me explain something. Until now, I've been talking about protons. Now I'm going to talk about nuclei. So if a nucleus has an odd number of protons, neutrons, or both, it has a magnetic dipole moment. If a nucleus has an even number of protons and neutrons and both, then guess what? No net magnetic dipole moment. Now I know some of you are asking, okay, I don't really understand this magnetic dipole moment business, but at least I understand that protons have a positive charge. Now you're saying that neutrons somehow factor into this. So how can neutrons that have no charge contribute to the magnetic dipole moment of a nucleus? And my answer to that is, I have no idea. So I don't understand this. If there's anyone who does understand this, then either speak up now, or if you're afraid that you're going to embarrass me, then come to me later. But I won't be embarrassed. So does anyone know the answer to this? Okay, well, if you can come to me later if you're worried that you'll embarrass me by saying this. At any rate, just be aware that any nucleus that has odd number protons, neutrons, both will have a magnetic dipole moment. And what that means is that some atoms, some elements have magnetic dipole moments. So which ones are they? Well, hydrogen has one. Helium does not, right? Because helium has 2 protons, even number. Fluorine 19 does. Sodium 23 does. Carbon 13 does. Oxygen 17 does. So even if you don't want to necessarily memorize the physics or understand the physics, you can sort of understand, at least memorize the concept that there are some elements that allow us, that can be seen with MRI, meaning that other elements cannot be seen with MRI. Now, different elements have different spins, and they're shown here in this table. By the way, Bill Bradley is an author on an excellent textbook on MR physics, Hashemi and Bradley. So if any of you would like to learn more about this, feel free to either purchase his book or email him and ask him whether he will give you his book for free. I am not an author on that book, so I don't have the ability to just give it to you. Now, notice that some things have a spin of a half, some things have a spin of 5 halves. Why is that? Again, I have no idea. But the proton that we image for clinical care 99.9999% of the time is hydrogen. So it's possible in research to image other things, and some of you in this room are probably actually imaging other things other than hydrogen, but at least for clinical MRI, as well as for fat MRI, as well as for MR elastography, as well as for LIRADs, as well as for liver imaging, again, I'm really trying to concentrate on the really important stuff, then we're going to be imaging hydrogen. Why hydrogen? Because we could do any element with an odd number of protons, neutrons, or both. So why do we pick hydrogen protons? Because almost every element. Why do we pick hydrogen protons? Because hydrogen is the most abundant. I guess what this is saying is that almost every element in the periodic table will have at least one isotope that we could, in fact, measure or look at with MRI. But why do we pick hydrogen protons? It's the most abundant. And just to show you how abundant it is, here are different nuclei that we could potentially look at with MRI. And if hydrogen has a relative content in the human body of 100%, you'll see that the next closest is 0.09%, and it gets even worse after that. So the point is, hydrogen is much, much, much more common, it's much more abundant by orders of magnitude than anything else. So if any of you have done MRI and you sometimes wonder why are these images so noisy, now imagine how much noisier they would get if we were trying to image the human body with something other than hydrogen. But which hydrogens? Any hydrogens? I mean, are we looking at the hydrogens in proteins? Are we looking at Are we looking at the hydrogens in the DNA? What hydrogens are we looking at? Turns out, for clinical care, we're looking at 2 hydrogens only. We're looking at the hydrogens in water. Those are the little red things attached to this oxygen. And we're looking at the hydrogens attached to carbons in fat. So the only hydrogens that we look at in clinical MRI are water hydrogens and fat hydrogens. And we don't look at anything else. All other hydrogens, amino acids, proteins, macromolecules, are invisible using conventional MRI. Now, I want to be clear. When I say they're invisible, I don't mean that they have no effect on the MR images. I mean that we don't see that themselves. Other things may affect the appearance of water and fat. So proteins, for example, can change the MR properties of water and fat. So water and fat in a proteinaceous fluid will look different than water and fat in a non-proteinaceous fluid. But what we're actually looking at is the water and the fat. Okay, so now let's take this very unhappy individual, and right now my guess is that probably applies to everyone here who's wondering, what am I doing in this room now? But so here you are, you're very unhappy, and you think you're unhappy because you're listening to me, but the real reason you're unhappy is that your protons are not aligned. Okay, so some of your protons are facing this way, some are facing, oh, my arrow, I just realized you cannot see my arrow. Okay, all right, well, I apologize about that. We're a little technical problem, so maybe after this lecture we'll see if we can sort that out. At any rate, you can see that there are proton magnetic dipole moments pointing in all sorts of different directions. And they're not just pointing in different directions, they're actually tumbling randomly. So let's take you and put you into a magnet. And once we put you into a magnet, you become very happy. And the reason you become very happy is instantaneously when we put you into that magnet, your protons will either align with or against the magnetic field. The magnetic dipole moments associated with each proton will instantaneously line up either with or against the magnetic field. Why is that? Quantum mechanics, so I don't know why, but they all line up with or against the magnetic field, and that occurs instantaneously. But instantaneously, it turns out that exactly half line up with and exactly half line up against. And that lining of half with and half against is random. Because half are lined up with and half are lined up against, initially, you in the magnet have no magnetic field associated with you because the ones lined up with cancel the ones lined up against. But they don't just line up, they also precess. So they precess at a particular frequency called the Larmor frequency. And that frequency of precession is proportional to the magnetic field. So B0 has 2 effects on protons. It causes the magnetic dipole moments of the protons to align with or against the magnetic field, and it causes the magnetic dipole moments to precess. Now notice in this diagram I'm showing a proton with its magnetic dipole moment, and I'm showing 2 kinds of rotation. One is the spin of the proton around its own, if you will, axis along its equator, and the other is the precession of the magnetic dipole moment. So keep in mind that these are not the same thing. There's the quantum mechanical property called spin, which is associated with the proton, and then there is the precession of the magnetic dipole moment of the proton. The spin is quantum mechanical, the precession is physical. So there is true precession of the magnetic dipole moment. Now that precession occurs at the Larmor frequency named after Joseph Larmor. And this is an equation that you should commit to memory. Luckily, it's a pretty simple equation. the frequency of precession is equal to something called the gyromagnetic ratio times the external magnetic field. And the gyromagnetic ratio depends on the proton. For hydrogen protons, it's 42.58 megahertz per Tesla. Now, you can plug in that formula, frequency equals gyromagnetic ratio times B0, into Excel or into your calculator. And pretty simply, you could make a table that shows you for different B naughts, 0.51, 1.53 Tesla, what is the frequency of precession. And you'll see that at 1.5 Tesla, the precessional frequency is 63.87 megahertz, TV channel 2. And at 3 Tesla, it's 127.73 megahertz, which is air traffic control. So why is this precessional frequency important? Because each nucleus has a unique gyromagnetic ratio, which means that for any given magnetic field strength, each nucleus has a unique resonance frequency. And that allows us to select what protons we want to excite. So I mentioned earlier that conceivably we could be doing MRI of hydrogen, or MRI of fluorine, or MRI of sodium, etc. But we want to do MRI of hydrogen. So if you're on a 1 Tesla scanner and you want to do MRI of hydrogen, you send radio frequency waves at 42.6 megahertz. If you want to, at 1 Tesla, image fluorine, you send radio frequency waves at 40 megahertz. So if you do radio frequency waves at 40 megahertz, you'll do fluorine MRI. If you do it at 42.6 megahertz, you'll do hydrogen MRI. And I know you guys are very smart, so now I'm going to ask you, if you wanted to image sodium at 1 Tesla, what radio frequency would you use? I bet everyone in this room can say 11.3 megahertz. So you see, this is not so hard, right? Okay, but we're going to do MRI of the liver, the most important organ in the universe, and so we're going to do 42.6 megahertz at 1 Tesla. Okay, I mentioned this before, a little semantics. Protons do not literally have spin. They're not literally spinning around their equator. They have a quantum mechanical property called spin. The spin is what accounts for the magnetic dipole moments. When placed in magnetic fields, the magnetic dipole moments precess, and this is a physical process. So the precession is a physical process, the spin is a quantum mechanical process. Okay, I mentioned earlier that instantaneously all the protons are lined up, magnetic dipole moments are lined up either with or against the magnetic field, but they don't stay that way. Over time, they start to line up with the magnetic field. So over time, some will start lining up with the magnetic field. How many? Not many. The net alignment is 3.4 protons per million per Tesla. So if you had 1 million protons and put them into a magnetic field, eventually a little more would align with and against, and you'd end up with, I don't know if I'm going to be able to do this right, but you can imagine that you would have 500,000 and 1.7 lined up with the magnetic field, and you'd have 499,998.3, or I'm getting confused, but you get the point that literally there'd be a difference of 3.4 out of 1 million lining up with or against. Imagine if you tried to do an election and you had 1 million people voting and the election came down to 3.4 people, okay? So that's how few protons net line up with the magnetic field. But that tiny little alignment makes the patient magnetized. So when you go into the MRI scanner, you become a magnet. The MRI scanner is worth $1 million. I will let you determine what your worth is, but you become a magnet inside a $1 million magnet. Now, why do these things start lining up? Because, and again, my arrow is not working, I apologize. initially, half are lined up against and half are lined up with. The ones that are lined up with are in a lower energy state. They're kind of going with the flow. The ones that are lined up against the magnetic field, the ones that are pointing down, those are in a high energy state. They're going against the flow. They're going against the tide, against the current. So, in order to reach equilibrium, some of those protons that are lined up against the magnetic field need to line up with the magnetic field and move down into a lower energy state, and then eventually there's an equilibrium. So now this system is in equilibrium. Now, this process of lining up with the magnetic field is called lattice relaxation. The protons, when they go from the high energy state to the low energy state, they release energy into the surrounding structure, which is called the lattice. So this is called lattice relaxation, and it's also known as T1 relaxation. So T1 relaxation, or spin lattice relaxation, is the release of energy from high energy protons as they transition to low energy protons from disequilibrium to equilibrium. So that's called T1 relaxation. Now that does not happen instantaneously. That follows a relaxation curve, which is an exponential. Now, Felix Bloch was a physicist who in 1948 published the famous, or 47, published the famous Bloch equations, named after him. He won the Nobel Prize in 1952. And I don't know if this is exactly the mathematical expressions he used, but the math that we use now is that the magnetic field strength is equal to the maximum magnetic field that you can achieve, which is m naught, times 1 minus e to the minus t over t1, or you can use the equation immediately below. Now, for some of the people in this room, this equation, they immediately understand what this equation looks like. There's probably 3 of you out there. For most of you, this looks like mumbo jumbo. So let's take this equation and plug it into Excel. So here's the equation at the top in yellow, and all I did is ask, what if t, little t, is equal to 0? Or what if little t is equal to this thing called t1? Or what if little t is equal to 2 times t1 or 3 times t1, etc.? And then these are the values you get: 0, 0.632, 0.865, 0.950. So what is this telling us? What this is telling us is that after 1 T1 relaxation time, you have recovered 63.2%. After 2 relaxation times, you've recovered 86.5%. After 3 relaxation times, you've recovered 95%. But there's something else here. Turns out that with every T1 relaxation time, you're getting 63.2% closer from where you are to equilibrium. So if you start out at 0 and equilibrium is 1, then after 1 relaxation time, you're at 63.2%. If you're at 63.2%, then you're going to go from 63.2% to 1%, and 63% of that is about, so you have 37% to go. 63% of 37% is about 22%, so that's what brings you up to 0.865. So every T1 time, you get 63% closer to equilibrium. So let's draw this schematically. On the y-axis, I'm showing magnetization, and on the x-axis, I'm showing time in the form of T1 times. So after 1 T1 time, I get 63% from 0 to equilibrium. After 2 relaxation times, I get 63% closer to that, and that brings me up to 86%. After 3 T1 relaxation times, I get 63% closer, and that brings me up to 95%. After 4 relaxation times, I'm at 98%, and eventually, after an infinite amount of time, I am at equilibrium relaxation. Now, different tissues have different T1 curves. So if we plot the signal intensity of different tissues as a function of time, you can see that fat at the top has the fastest T1 relaxation time. Pancreas and liver are second and third. Then comes muscle, then comes spleen, and then comes pure water. So these are T1 relaxation times of the abdomen at 1.5 Tesla. So in the abdomen, fat has the fastest relaxation time, water has the slowest. The spleen behaves a lot on MRI like a metastasis. So often the spleen is considered a surrogate of a metastasis. So you can, if you substitute metastasis for spleen, you would sort of see the T1 relaxation time that you might expect for your average metastasis. I mentioned before that the net alignment is only 3.4 protons per million. It's a very, very small amount. So how is it with such a small alignment that we can see anything with MRI? And for that, we have to thank Avogadro. So Avogadro, remember Avogadro's number from high school? 6.02 times 10 to the 23 molecules per mole. So in other words, if we have 1 gram of tissue, and that gram of tissue is 60% water, which we can see, 20% fat, CH2, which we can see on MRI, and 20% invisible, that's proteins, amino acids that we can't see, then just with a few back-of-the-envelope calculations, we can figure out that even though the net alignment is only 3 per million, there are so many protons in 1 gram of tissue that we still can see over 10 to the 17 protons per gram of tissue. So it's because there's so many protons that we can see anything even though the net alignment is so low. Now this net alignment has a name, and I maybe didn't make it clear earlier, but this net alignment is called M naught. So the external magnetic field is called B naught. The magnetic field that's induced in you when you go into an MR scanner is M naught. Now M naught is very, very tiny compared to B naught. So B naught is the external magnetic field. M naught is your magnetic field when you go into the magnet. And it is very tiny. It's about 1/10,000th the size of B naught. And it's proportional to B naught. So let me pause there for a second. M naught is proportional to B naught. So when you go into a 1.5 T scanner, you are half as strong a magnet as when you go into a 3T scanner. Or stated differently, when you're in a 3T scanner, you're twice as strong a magnet yourself as when you go into a 1.5 T scanner. So we'll get back to that in a second. What I want to emphasize right now is M naught is very tiny. So how tiny is tiny? This is how tiny tiny is. So if you go into a magnetic field that has the surface area of B naught, then your surface area magnetic field is that. So in other words, these arrows, the surface areas of these arrows are proportional to your magnetic field. So you can see that the $1 million magnet, B naught, is much, much, much stronger than you are. You're a puny little magnet inside this very strong magnet. And somehow we have to detect your puny little magnetic field from this giant monolith. How are we going to detect your puny little magnetic field? Well, your puny little magnetic field is the source of all MR signals, so we somehow have to see it. So how do we see it? Turns out that we can't measure it directly. It's too small, and it's pointing in the same direction. So to see it, we have to flip it into the perpendicular plane, and that requires energy. And that energy is going to come from radio frequency energy. What frequency? If you're at 1.5 Tesla, it's going to be TV channel 2. And if you're at 3 Tesla, air traffic control. So it's either going to be 63 megahertz or 127 megahertz. And when we apply radio frequency waves, we can take your puny little magnetic field and we can tip it. Now, some of you probably didn't notice that that little arrow tipped, but maybe Jen noticed. I don't know. She's the only person who might have noticed because she's the only person close enough that that arrow tipped. So trust me, that little arrow just tipped. So now let's look at that tiny little arrow. Now let's magnify. And so we're going to start with M0, which is now the light blue arrow pointing up inside the giant arrow of B0. So there is the light blue arrow pointing up is M0. Let's get rid of the magnetic fields because it's distracting us, and let's focus on M0. So here is M0 or MZ. It's the magnetic field pointing in the Z direction. That's your magnetic field after you have reached equilibrium. And now what we're going to do is we're going to send a radio frequency pulse at the Larmor frequency, and that is going to induce a new magnetic field called B1. The B1 magnetic field is going to be perpendicular to the external magnetic field, which is pointing in the Z direction. Now, I mentioned earlier that magnetic dipole moments like to precess around B0. So it turns out that MZ, this light blue arrow, also likes to precess. And it's now going to precess around B1. And it will now precess into the XY plane. So the radio frequency pulse is now going to cause the magnetic field, the net magnetic field in your body to now tilt into the XY plane. And that magnetic field is now in the XY plane, so we call it MXY. And MXY is now going to precess around B0, which is pointing in the Z direction. So this is now going to precess around that direction. Now let's look at it from the top. So what we're showing now is MXY in the XY plane. And this light blue arrow is going to be precessing around B0, which is pointing in and out of the screen. If there was no dephasing, this thing would precess forever. So if there was no such thing as dephasing, this magnetic dipole, which is now in the XY plane, would just basically precess forever. But it turns out there is dephasing because this net blue arrow is created by multiple smaller arrows, and over time that will dephase and lose signal. And the loss of signal is known as T2 relaxation. So let's see if I think this is going to try to explain it. So basically what I'm trying to show here is that the reason we lose signal is that the individual arrow, let me go back for a second, let's see if I can explain this again. So what I'm trying to show here is the light blue arrow is the net magnetic dipole of all of your individual magnetic dipoles, meaning the individual protons. So superimposed on the light blue arrow is a red arrow. Initially, in fact, there's many red arrows. Initially, all the red arrows are pointing in the same direction. But over time, these little red arrows start to precess at slightly different frequencies. And when they precess at different frequencies, the net vector gets smaller and smaller. And we lose signal, and that loss of signal is known as T2 relaxation. So the T2 relaxation was also described by Felix Bloch in 1947 or 48 with a Nobel Prize in 52. And here are the equations for T2 relaxation. Same principle as before. Some of you look at these equations and you can immediately picture what this looks like. But most of you probably can't. I certainly can't. And so I did the same little, I don't know if I should call it an experiment, but I did the same calculation on Excel. And I just plotted different T2 relaxation times in the left-hand column. And on the right-hand column, I just simply calculated how much signal would I have if I started with 1 and I was heading to 0. And just like with T1 relaxation, we are gaining 63% of the signal at every relaxation time. Now we're losing 63% of our residual signal with every T2 relaxation time. So if you start out with a signal of 1 and you lose 63% 63% of your signal, you're going to go to 36.8% of your signal. If you then lose 63% of your remaining signal, you're going to go to 13.5%, etc. So every T2 relaxation time, you get 63% closer to equilibrium. And just like with T1 relaxation, we can do the same thing with T2 relaxation. So we start at the asymptotic line. After one relaxation time, we lose 63% of our signal, brings us down to here. We have 37% of our signal left. We then lose 63% of that. And when we lose 63% of that, it brings us down to 86% loss. We now have 14% of our signal left. We lose 63% of that. We get down to 95% signal loss, etc., etc. And after an infinite amount of time, we have zero signal. And just like we look in tissues and calculate their T1 relaxation times, we can also calculate their T2 relaxation times. So remember that water had the slowest T1 relaxation time. Water has the slowest T2 relaxation time. So water is the slowest to recover, but it's also the slowest to lose signal. And you can see that the liver, which was one of the fastest organs to gain signal, is also one of the organs that loses signal most rapidly. Okay, so why do protons dephase? I mentioned that protons are dephasing. Why does this happen? Why do we get dephasing? We get the dephasing for one reason and one reason only. The protons experience different magnetic fields. Remember the Larmor equation? The precession frequency of a proton is proportional to its magnetic field. So, if every proton experiences a slightly different magnetic field, it will precess at a slightly different frequency. And if they're all precessing at slightly different frequencies, they eventually get out of phase with each other. Okay, so that's the key thing to remember from this slide. All sources of dephasing are because the protons are experiencing different magnetic fields. Now this of course begs the question, why are they experiencing different magnetic fields? Two reasons. One is random fluctuations in the magnetic field caused by random interactions of protons with each other. The other, so random fluctuations caused by random interactions. The other one is not random, the other is static or fixed fluctuations caused by static or fixed imperfections in the magnetic field. So for example, if your $1 million scanner is imperfect, there will be a fixed imperfection in the magnetic field. Alternatively, if you have a couple of iron particles in your liver, for whatever reason, assuming those iron particles aren't moving around, and no reason why they would, those iron particles are going to be causing fixed or static fluctuations in the magnetic field. The random ones, because they're random, they're not reversible. Once you lose the signal due to a random fluctuation, you can't reverse it because you can't undo the random interaction. However, the fixed, static, non-random fluctuations are reversible, and they're reversible with a refocusing pulse. Now, I'm not going to get into the details of what a refocusing pulse is, but for now just know that random fluctuations are not reversible because the random interactions cannot be reproduced and negated, but the static, non-random ones can be reversed. When you when you do spin echo images, you reverse the random fluctuations, and the only causes of signal loss, when you do spin echo images, you reverse the static fluctuations. You can't reverse the random ones. So spin echo images lose signal due only to random fluctuations. Gradient echo images, on the other hand, don't correct for anything. So gradient echo images lose signal due to random fluctuations and static fluctuations. Now I realize that a lot of this sounds like a bunch of mumbo jumbo, so let's just take a step back for a second. Spin echo images lose signal only due to random fluctuations. Gradient echo images lose signal due to random fluctuations and static fluctuations. So even if you have no idea what a static fluctuation is, and even if you have no idea what a random fluctuation is, you can imagine that since gradient echo images lose signal due to both, and spin echo images lose signal only due to one, all other things being equal, spin echo images will have more signal than gradient echo images. So even if you understand nothing else other than one thing is losing signal due to two things, and one thing is losing signal only to one thing, the thing that's losing signal due to two things will have less signal, all other things being equal. Okay, so we're not going to talk too much about T2 star right now, but we'll talk a little bit about T2. Why do protons have these random interactions? Because protons can either have positive or negative magnetic dipole moments. You can imagine that a proton that has a positive magnetic dipole moment, the one on your left, will slightly increase the magnetic. I think I drew this incorrectly, sorry, there's an arithmetic error here. So on the left, we have a proton that's lined up with the magnetic field. So the local magnetic field that proton 1, or that something next to proton 1 is experiencing, will be a little bit bigger than the net magnetic field. Proton 2 is pointing against the magnetic field, so the local magnetic field in that area will be a little bit lower than B0. So in other words, you can think of the local magnetic field as being equal to the big external magnetic field plus whatever effect the proton magnetic dipole moment has on it. If it points up, it increases it, points down, it decreases it. If you're not following all these details, don't worry about the details. The point is that the protons, by virtue of being tiny magnetic fields, can alter the local magnetic field. So why does that lead to signal loss? Well, because the protons can interact with each other to increase or decrease their local magnetic fields, and they can either precess faster or slower depending on how they're interacting. Now, water molecules spin around so fast that the protons don't interact with each other very much at all. So there's very little signal loss in water due to these spin-spin interactions because the water molecules are moving around too fast. In soft tissues, the protons are moving around more slowly, and so they have more time to interact. So in soft tissues, we lose signal more rapidly. And in solid tissue, the protons move around so little that they're just vibrating next to one another. They very strongly affect their magnetic fields, and you have a lot of signal loss. Okay, just a few more slides to go. Let's talk now about this thing called chemical shift. So what do we mean by chemical shift? What we mean by chemical shift is that the frequency of precession of protons depends on their chemical environment. So depending on their chemical environment, the frequency might shift. So let's start with water on your left. Oxygen is a very capitalistic nucleus, and it hogs the electron cloud to itself. So the hydrogen protons in red that are attached to oxygen feel the full bore of the magnetic field. However, carbon, which is on your right, is a very communist nucleus, and it shares its electron clouds with its neighbors. So now let's look at water on the left, and you can imagine that that proton is experiencing the full brunt of the magnetic field because the electron cloud is not shielding it. What about fat? In the fat molecule on the right, the hydrogen protons are shielded from the magnetic field, and so those protons do not experience the full magnetic field. Water protons precess very fast, fat protons precess a little bit slower. The difference is very small. The difference is 217 hertz at 1.5 Tesla, which is, and the difference is 434 hertz at 3 Tesla. So this is a difference of 3.4 or 3.5 parts per million. Now, why is this relevant? Well, let's talk a little bit about something called chemical shift artifact. Now, I mentioned earlier that in MRI, we're going to either be imaging water, which is the image at the top, where water-based structures such as the liver, the spleen, the kidneys look bright, but fat, the stuff in between, looks dark. Or we're going to be imaging fat, like the image below, where the fat is bright, but the water-based structures such as the liver, the pancreas, the spleen are dark. So in MRI, we're going to be imaging water, and we're going to be imaging fat. And when you see an MRI image, it's actually the summation of these two separate images. So you can think of MRI as capturing a water image at the top and a fat image below, but the two images are blended together like this. So far, so good. But now, let's remember that when we get an MR image, we have to apply something called a gradient in the frequency encoding direction. So we apply the gradient in the frequency encoding direction in order to know where protons are in the frequency encoding direction. So some of you, this is review, for some of you this might be mumbo jumbo. So if it's mumbo jumbo, don't worry too much, but just for now, just remember that in MR, we're going to have a water image and a fat image, and they're superimposed. And then we're going to add a gradient, and that gradient is going to change the magnetic field. Now remember that protons precess at the frequency of the magnetic field they experience. But water protons will experience a greater magnetic field than fat protons because water protons are not shielded by the electron cloud, but fat protons are. So now you can imagine that the water image is going to shift to the left relative to the fat image because the water protons are precessing a little bit faster than the fat protons. And if you sort of imagine what it would look like for the water image to shift, then you get chemical shift of the first kind artifact, where on one side of the structures you see summation of water and fat, which causes brightening, and on the other side you see a signal void because the water has shifted out of that location and the MR scanner thinks there's nothing there. So this is chemical shift of the first kind. There's also something called chemical shift of the second kind, and that has to do with the fact that water, again, it has to do with the fact that water and fat are precessing at different frequencies. So they start out at the same frequency, water in blue and fat in yellow. They're precessing at the same frequency and they have signal. But over time, because water is precessing more slowly than fat, periodically water is going to be out of phase with fat and periodically be in phase. So when they're in phase, they sum up, and when they're out of phase, they cancel, and you get this oscillating signal, IP, OP, IP, OP, IP, etc. So the point is that when fat and water are in phase, they add up. When fat and water are out of phase, they cancel and you lose signal. So we can get images now where fat and water are out of phase, such as the image on your left, and we can get images where fat and water are in phase, where they add up. And that's why the liver looks darker on the image on your left than it does on the image on your right, because this is a fatty liver, and the fat and the water are canceling out due to this out-of-phase phenomenon. Now, the last thing I want to mention is that we talked about chemical shift artifact of the first kind when the water image got moved relative to the fat image. Now I want to explain this chemical shift of the second kind, which is this India ink artifact. So here we have water and fat superimposed, and let's impose now a grid of voxels on this. And you can imagine that some of these voxels contain only water, some of these voxels contain only fat, but can you guys see that some of the voxels along the edges of the organs contain partly fat from the outside and partly water from the inside of the organ? So wherever we have an interface between a water-based organ and surrounding fat, those voxels will contain both fat and water, and on an out-of-phase image, they will cancel, and you'll get this India ink artifact around those boundaries. Now, you'll notice that this is an incomplete drawing. I did not actually blacken every interface. It actually took me an hour to do this, and I finally lost patience. So by the end of my career, every one of those interfaces will get colored in, but it might just take a while for me to do it. But hopefully you guys can get the point. Okay, so let us now sum up. And I'm sorry that I went a little longer than I meant to, and I'll try to speed things up a little bit for the lectures that follow. What did we talk about today? So today, or this morning, or this first lecture, we talked about the electromagnetic spectrum, and we mentioned that the electromagnetic spectrum includes X-rays, it includes UV light, it includes infrared light, it includes microwaves, and then somewhere in there it includes TV and radio waves. And MRI is in the TV and radio wave part of the electromagnetic spectrum. It will have wavelengths on the order of about a meter. And if you're doing 1.5 T MRI, you'll be at about TV channel 2. And if you're doing 3T MRI, you'll be at about air traffic control, 63 megahertz, 127 megahertz. We also talked about this thing called B naught, that we're going to put you or the patient or the tissue specimen into a very powerful magnetic field, and that magnetic field is known as B naught. The unit of B naught is Tesla. We also talked about protons, that in MRI we image protons. What protons do we image usually? We image hydrogen protons. Why hydrogen? Because they're so common. Do we image all hydrogen protons? No, we image the hydrogen protons in fat and water. We do not image the hydrogen protons in proteins or DNA or cell membranes. Do proteins affect the protons in water and fat? They might. So we might see them indirectly, but we're not imaging them directly. We mentioned that protons have this magical or quantum mechanical property called spin that can either be positive or negative, and that nuclei that have an even number of protons, neutrons, or both will have a net magnetic dipole moment. The magnetic dipole moment is created by the quantum mechanical spin. These magnetic dipole moments, when placed in an external magnetic field, will line up with or against the magnetic field, and over time they will reach an equilibrium. And once they reach an equilibrium and you have a net number of magnetic dipole moments lining up with as opposed to against the magnetic field, they will create their own little magnetic field called M naught. M naught is very tiny compared to B naught. It's about 1/10,000th of B naught. And that little puny M naught is going to be the source of all MR signal. Now, the magnetic dipole moments don't just line up, they also precess, and they precess at a particular frequency called the Larmor frequency, which in turn is determined by something called the gyromagnetic ratio. Every type of proton has its own gyromagnetic ratio. So hydrogen protons have a gyromagnetic ratio of 42.6, fluorine protons have a magnetic ratio of 40.0, etc. If you want to talk to hydrogen protons, use the radio frequency pulse that corresponds to hydrogen protons. If you want to talk to fluorine, use a different radio frequency. These protons, or these magnetic dipole moments that initially are lined up with or against the magnetic field, will over time line up with the magnetic field by losing energy to the so-called surrounding lattice, and that is known as T1 relaxation or spin lattice relaxation. T1 relaxation is governed by an exponential equation that was defined by Felix Bloch, and according to T1 relaxation, every T1 time you go from where you are towards equilibrium by another 63%. So after one T1 relaxation time, you're 63% recovered. After 2 relaxation times, you're about 85% recovered. After 3 T1 relaxation times, you're 95% recovered, etc. Different tissues have different T1 relaxations. The tissue in the abdomen that has the fastest T1 relaxation is fat, and then pancreas, and then liver. And the thing that has the slowest T1 relaxation is pure water. The spleen has low T1 relaxation, but not quite as low as water. And the T1 relaxation of spleen is about the same as the T1 relaxation of a prototypical metastasis. Now, M naught is very puny. So how do we see M naught? We got to tip it into the XY plane. We got to tip it so that it's perpendicular to B naught. How do we do that? We send in a radio frequency pulse. What frequency? The frequency governed by the gyromagnetic ratio, the Larmor frequency. So then we tip M naught into the XY plane, and it starts precessing, and I didn't make that clear earlier, but it's precessing, and that precession gives off radio energy that we can then detect. The problem is that that energy dissipates over time because that initial transverse relaxation is the vector sum of multiple individual magnetic dipole moments, and over time those magnetic dipole moments lose coherence, they dephase. Why do they dephase? They dephase because they're experiencing different magnetic fields. Why are they experiencing different magnetic fields? Two reasons. There may be fixed or static imperfections in the magnetic field. For example, there may be iron particles in your liver which cause the magnetic field to be heterogeneous. But also, the protons interact with each other. The protons can be pointing up, they can be pointing down. So two protons both pointing up increase the magnetic field. Two protons both pointing down decrease the magnetic field, etc. So these protons actually affect the magnetic field, and they affect each other. If they're moving around very, very fast, they don't affect each other very much. And if they're moving around very slowly, they have lots of time to interact and to affect each other. So water, in which the molecules are moving around very, very fast, the protons don't have time to interact very much, and therefore there's not much signal loss due to this mechanism. So water has the slowest T2 relaxation, whereas more solid things such as fat have faster T2 relaxation. And the liver is one of the organs that has the fastest T2 relaxation. Back to the spleen has a T2 relaxation, sort of like a metastasis. So why am I emphasizing the spleen in this? Because if you're interested in optimizing MR imaging, if that's something you're interested in doing, then one option is to recruit a volunteer who happens to have metastases and tweak your sequences so that you can see the metastases better. But many patients with metastases probably won't respond very favorably to you calling them up and saying, Mr. Smith, I know that you have metastases and you're going to die in a couple of weeks, but I was thinking that you might want to come in so I can optimize my scanner. Would you mind doing that? So they may not like that. Instead, you can turn to your buddy and say, you're a perfectly healthy person, but you have this surrogate of metastasis called the spleen. So let me put you in the scanner, and I'm going to see what can make the spleen look different than your liver, and that's one way of optimizing your sequences by recruiting a healthy volunteer. We then talked a little bit about chemical shift, and the key thing with chemical shift is that water protons are shielded from the magnetic field, but fat protons are not. So water protons spin faster than fat protons. Because water protons spin faster than fat protons, they will periodically be in phase and periodically be out of phase. So if we get in phase images, fat and water add up. If we get out of phase images, fat and water cancel. And that leads to certain artifacts. One artifact is called chemical shift of the first kind, and one is chemical shift of the second kind. I don't care whether you remember what's first kind and second kind, because that's just memorization. What I do care about is that you know the concept. So in one kind of chemical shift, water and fat are shifted in space relative to one another, and that leads to this sort of boundary phenomenon of having a bright line on one side and a dark line on the other. So that's called spatial misregistration chemical shift. The other kind of chemical shift is wherever you have a fat-water boundary, you're going to lose signal on the out of phase. That's the India ink artifact. That's the phase cancellation type of chemical shift. Okay, so this was probably, at least for me, this is the most difficult lecture because this is not, I'm not a physicist. MR physics is not my area of expertise. So I want to thank you for bearing with me as I sort of struggled through this. I hope some of this was useful to you. If I said anything that was grossly incorrect, please do correct me afterwards. I know all of you are nice people and don't want to embarrass me in public, but if you know that I said something incorrect, please do come up to me afterwards. Okay, why don't we take like a 5-minute break, because that was probably a headache, and then we'll move on to the next headache, which is going to be image optimization. And then after that, things get easier for me. Thanks.